A rod AB of length 15 centimeters rests in between two coordinate axes. This is done in such a way that the endpoint A lies on x-axis and the endpoint B lies on y-axis. A point P, x, y is taken on the rod in such a way that AP is equal to 6 cm. Show that the locus of P is an ellipse. Pause the video, give this a try. Okay, so let's break down what's happening. There's a rod AB of length 15 centimeters. This rests between the two coordinate axes, the x-axis and the y-axis. Now it moves. It moves in such a way that the endpoint A lies on the x-axis. So this point stays on the x-axis, and this point B, it stays on the y-axis. So think of this rod as sliding between these two axes. Now there's this point P on this rod such that AP, this length, is 6 centimeters. So basically move along the rod 6 units from this point to get to this point. And we need to observe this point. When this rod moves, what's the path that this point is taking? The question says that we have to prove that the locus of P is an ellipse. When this point moves, it moves on the ellipse. Now before we prove this, let's actually see this in action. When the rod moves, can you see that this point moves along the ellipse? Do you see that the shape is an ellipse? Well, it's not quite clear, but it does take the shape. It goes from this point. Let's see this again. It goes from this point to this point. So it does take a curve. Now let's add the ellipse here. Now let's see it. This time it's much more clearer. This point is always on this ellipse. So yes, the locus of this point when this rod moves is an ellipse. All right, so how do we prove this? If you want to try this on your own, pause the video, give this a shot. Okay, let's do this together. In questions like these, it's best to assume a variable that's always changing and then eliminate that variable. So this rod is 15 units. Let's say that this angle is changing. Let's say that the angle that the rod makes with the floor, this angle is theta. When theta changes, this rod slides and this point moves. So let's try to find the coordinates of this point in terms of theta. And then we'll worry about eliminating theta later. So if this is 15, in this right angle triangle, we can apply trigo. This base is 15 cos theta and this height is 15 sin theta. In this smaller right angle triangle, the angle is theta. This is 90. What's these two lengths? This is 6. As the question says, this length is 6 units, which means this is 6 cos theta and this is 6 sin theta, exactly in the same way as we've done in the larger triangle. Now using these lengths, can we figure out the coordinates of this point? Let's see. What's the x coordinate? If this entire length is 15 cos theta and this length is 6 cos theta, this must be 15 minus 6, that's 9 cos theta. That's the x coordinate. And what's the y coordinate? Well, that's this length, that's 6 sin theta. So the coordinates for this point are 9 cos theta and 6 sin theta. This is x, y. So the coordinates of P are 9 cos theta and 6 sin theta. When theta changes, the coordinates of this point change. But how do they change? Let's connect them. If x is 9 cos theta and y is 6 sin theta, let's try writing cos theta and sin theta in terms of x and y. Cos theta is x by 9 and sin theta is y by 6. Now how can we eliminate theta here? Well, we know one identity. Sin square plus cos square is equal to 1. That works for every angle, which means it works for this angle as well. So cos square plus sin square is 1, which means x by 9 squared plus y by 6 squared, that's equal to 1. If we square this, we get x squared by 81 plus y squared by 36 equals to 1. And just by observing this equation, we can say that, yes, the locus of this point is an ellipse, because this is an equation of an ellipse. Let's try one more. We have a rod of length 12 centimeter and it moves with its ends always touching the coordinate axis. Let's see this move. Let's see this in action. This is how this rod is moving. This end is always on the y-axis and this end is always on the x-axis. Let's see this again. Okay. This is how this rod is moving. We need to determine the equation of the locus of the point P on the rod, which is 3 centimeters from the end in contact with the x-axis. So we need to figure out the locus of this point, which is 3 units from this end. All right. As we can see that the locus is an ellipse, but let's actually prove it. Let's actually find its equation. If you want to pause the video and try this on your own, feel free to do that. Okay, let's do this together. We apply the same thing that we applied in the previous problem. This entire length is 12 units and this is 3 units. If this angle is theta, this base is 12 cos theta. This length is 3 units, which means the coordinates for this point are going to be, this length is 3 cos theta. So 12 minus 3 is 9 cos theta. That's the x coordinate. And the height is going to be 3 sin theta. So the point is 9 cos theta, 3 sin theta. This is the coordinate for the point P. Now let's eliminate theta. X is 9 cos theta and y is 3 sin theta. So cos theta is x by 9 and sin theta is y by 3. If we square and add, we'll eliminate theta. So x by 9 squared plus y by 3 squared, that's equal to 1. Or x squared by 81 plus y squared by 9, that's equal to 1. This is the equation of the locus of this point, which as we can see is an ellipse.